Physics Bites,
a science podcast in English
by the students of Notre Dame d'Ascension.
Hello and welcome to Physics Bites, the English language physics podcast of the students of Notre Dame d'Ascension here in Paris. Welcome to a new episode. We have two new students today. We have Marguerite and Mathis, who have both been my students for the last couple of years, who are going to be talking to us about the end of the universe. Is that right?
Yes.
Yeah, it is.
All right. So it was one of the, I found more interesting, very original presentations that you guys did. We really enjoyed it a lot. So let's start by you guys maybe introducing yourselves, and then we'll get right into the heart of the subject. Who wants to start?
I'm starting.
Hi,
So my name is Mathis.
Yeah. So just to be sure, you both have been students of mine for the last 3 years, but neither of you guys are actually doing physics this year.
No.
Okay. What are you doing this year, Mathis? Your majors?
I'm doing economics and geopolitics.
Right. And Marguerite, what are your majors?
The same.
All right. So at the end, I'm going to ask you guys what made you pick this topic, but maybe we'll just get right into it. So maybe Marguerite, you can start, and then you can go back and forth between the both of you. What was your topic about?
The main topic was about the end of the universe, and I talked mainly about one theory, the Big Freeze theory, that is now the main theory and the most plausible one about how the universe could end. So the Big Freeze is also called the heat death, and it's the idea developed since the 18th century that the universe could end as a big cooling down of its global temperature. So this really cooling down could lead to the end of life, the end of activity.
Right. So when you're talking about cooling down, there's a lot of thermodynamics, and you guys did a really, really, really good job of talking about some of the more fundamental and basic notions of thermodynamics. But first of all, do you guys, maybe before we talk about the end of the universe, maybe the end of the universe is kind of related to the beginning of the universe. So do you want to maybe talk a little bit about the beginning of the universe before we concentrate on how it's all going to come to various kinds of ends?
I guess it's all linked with entropy. I mean,
the question of entropy.
This is really the main action, the main law of thermodynamics that drives everything from the creation to the death of the universe. And it is the important points that led all our reflection around the end of the universe.
So what is entropy? You guys did a really... it's unfortunate we can't have the visuals, because you guys had really, really good visuals when you were talking about what entropy is, but I'm sure you can do just a good job just talking about it.
Yeah, we're going to try to describe it. So entropy, if I have to define it simply, it's like the measurement of disorder. How the energy is spread out by the matter. So it's described why ice melts, why cream spreads in coffee, and why air leaks out of a tire. So it's a really important law of physics. And more than measurement of disorder, we can think about it through probability, and it is where it's going to be a bit more complex.
Okay. So you talked about it's a measure of disorder, it's related to probabilities. Can you give us a very basic idea of what is the link between disorder and probabilities, maybe?
In fact, energy is contained into matter, and energy can be dispatched in matter with a lot of options that are called microstates. So this sum of energy that we call quanta can be in many different microstates, and this is where the probability is involved. because some of the energy configurations, some of the microstates, have higher probability of occurring than other. So matter can be dispatched with a higher probability than another way.
Right. So just to sort of help understand what we mean by microstates, the idea is that this is something that's particularly applicable when we have large numbers of things, which is the case for matter, which is made up of tiny atoms, and we have billions and billions of them. And then what you talk about when you mention microstates is kind of the idea of how they can sort of be configured together. Are they configured in a very specific way, which is very unlikely? Or are they configured in a way which has a high probability but is a very sort of homogeneous, even spread of things? Is that a good idea? Okay.
Yeah.
So what is the link between entropy, probabilities of these different microstates, and like the idea of heat and thermodynamics? Because that's where we're heading for.
The probability of the energy spread is linked, for example, with all the stars that are dispersing their energy through light, for example. And on a bigger scale, we can see that all the universe is tending to a state of maximum entropy, to a state of a maximum energy spread, where all the energy is spread out through light, heat, and microwave, and etc. And this is where the probability of a small at a small scale could be extended to the bigger scale, to the scale of the universe, and it can be calculated through that.
Okay. So, just to give maybe a visual sort of idea of what we mean is, for example, when you put a drop of milk into coffee, the original configuration is a microstate which is very specific. You have all the milk in one space and all the coffee in the rest. And that, you're saying, is not the most probable state. The more probable state is that the coffee spreads everywhere and the milk spreads everywhere, which is what happens if we just let the coffee and the milk together. So the way the universe is going to go in general is towards the state where everything is kind of spread and mixed and you can't tell one spot from another. Is that it? Yeah,
it is. Or if you want another picture or description, you can talk about sand. And if you put energy to create a castle, you have to continuously bring energy and just bring energy to maintain a state of order. If you want it if you stop providing energy, the sand returns to its original high states. Okay. It's the same for a star or any object or matter. It has to provide energy to counter the entropy, or it will just tend to a state of mess.
Okay, and to sort of close the book on this question of entropy, which is not the main topic of your presentation, but sort of a necessary tool that is going to be used, this is sort of what you said physicists use to describe what we call time's arrow. Do you want to maybe briefly tell us what we mean by time's arrow and how it links to this, and then we'll go to some of the more specific theories.
So time's arrow is like a one-way direction in which time appears to flow, like from past to present to future. Right. And why do we use entropy? So the second law of thermodynamics states that entropy never decreases, like we said. But since entropy increases over time, we can use it to define a direction for the time itself, like the past from the future in decreasing entropy. Okay. So maybe now that we've sort of established this sort of the idea that the universe has a direction that it evolves in through time, so that we can define what is the beginning and what is the end, let's maybe turn to Marguerite, who you talked about a couple of ideas that were at the origin of a lot of these things. Do you want to maybe talk a little bit about that?
Yes, so like Mathis said, entropy is really key to how also it began with the Big Bang. So because to understand the end of universe, we have to really see how it began. So with the Big Bang, the universe was really hot, and the density was really high. So the planet would really be held together, and so the planets were forming and everything. So the universe was really young, and from time to time, the universe starts losing density because of dark energy. So dark energy is repulsive to gravity on the large scales, so it makes the universe more dilute with less matter. So in billions of time, the universe will have so much diluted that there will be no more gravity and no more energy. So the planet will start evaporating, and in the end, we will just have black holes. And no more life, and black holes will start themselves evaporating thanks to Hawking radiations.
Right. Now hold on, because you're mentioning a lot of different topics that we're going to get into. Hawking radiation and black holes and stuff like that. Just as a note, if listeners are interested, last year we did have a really good podcast on dark energy and dark matter, which are two very different things. But this idea of dark energy is interesting because it is a theory. We haven't really confirmed it, and yet it would help explain a lot of phenomenon that we have observed. But let's go back to the idea of the origins of universe, the idea that the universe is expanding. Why do we believe that the universe is expanding? Where does that idea come from, and who came up with it? And maybe you can just talk maybe 1 or 2 minutes about that.
So the idea of the expansions of the universe is related to, I think, maybe Einstein's theories.
Right, so Einstein's theory of relativity, which sort of explains the way gravitation works at a cosmic scale. And also, maybe you came across the work of Hubble when you were doing some research?
Yes, Hubble, yes.
Right. What did Hubble do? Where is Hubble's contribution to all this? Do you remember?
Not really precisely, but...
So he was more about the observation that the universe is expanding. The universe is expanding. Yes. He observed that every star, every galaxy in every direction is always going away from us. And so that kind of broke the status quo idea at the time that the universe was sort of steady and not changing. However, he showed that no, the universe is actually expanding. And if it's expanding in every direction, then it means that it's kind of like a bubble that's going bigger and bigger. And that's the idea that if going forward in time, the universe is getting bigger. If you go backwards in time, it has to get smaller. And if it gets smaller, it just means that there was a starting point, which would have been the idea of the Big Bang.
Okay, yes.
Okay. Do either of you maybe want to talk about, you mentioned the 5 ages of the universe. Who wants to talk about that a little bit?
Yes.
Marguerite, do you want to talk about
I
it?
can, yes.
Okay, go ahead.
So there is a book published, I think, in the beginning of the 21st century that said that the universe has 5 states, but it's like a classification of the time, and it's not really recognized by everyone, but it is really helpful to help us understand how the universe lived in the past and will live in the future.
Okay, so just give it a very short summary what the 5 ages are, and like what is the specific characteristic of each of these ages, maybe.
Yes, so the first era is the primordial era, and it's just after the Big Bang, and it's where the first isotopes were created, such as helium, and so it's the first really molecules and atoms that were combined together. Then we have the Stellarius era, which begins around 300 million years, and it's the era where the entropy starts to decrease a bit, and the matter is really organizing itself.
Just one question, Marguerite.
Stars, yeah.
Do we have an idea of currently how old we think the universe is?
13.8 billion years.
Right. So which means that we're still in the Stelliferous era. Is that it?
I think we are still in the Stelliferous era because
So out of the 5 eras that you're going to explain to us, we're still in the second stage. So a long way to go.
Yes.
Okay, I'll let you continue. So you said the second era was between 300 million years after the Big Bang to 10 to the power of 14, which is kind of around where we are, where you have galaxies and stars forming, and then the third stage.
It's the degenerate era. It will last until 10 power 39 after the Big Bang, and it's really interesting for the Big Freeze because it is the moment where white dwarfs, black holes, and all the protons. So white dwarfs are like stars like sun that are dying and becomes dwarfs. And all those elements with black holes and protons will just start to decay, and the universe will really start to becoming more and more cold. And so just after this era we have the black holes era that will last after just until 10 power 100 years after the Big Bang. So in this era only just black holes would stay, but eventually they will start to evaporate due to Hawking's radiations. And then we have the dark...
The final era.
Yeah. So the last era is the dark era, and it will really not stop because it's the end of life as we know it, because only minimal particles will remain, such as photons and leptons, and so they are subatomic, and they will just not be as much as powerful as really atoms or molecules. So there will not be life, and because they will not never be in contact with the others. So the universe will just be in a state of non-activity.
Okay, so of course, when we're talking about numbers like 10 to the power of 100 or above 10 to the power of 100 years, this is just, it might as well say infinite, just because these numbers are so beyond the scale of human understanding. But it's a very speculative way of looking at things, but it's based in proper physics that we've tested, theories such as the theory of relativity, which explains gravitation at cosmic scales. So it's not just science fiction. It's not just fiction, it's more science. Okay.
Yes.
So, shall we get into some of the potential endpoints for the universe, maybe? Maybe we can come back to Mathis a little bit and come back to the idea of entropy, because you talked about life as a manifestation of entropy. That was the sentence you had. Do you want to maybe develop that idea, elaborate a little bit for us?
Yeah, I can. So for a long time we thought that life was kind of against the second law of thermodynamics, so against entropy. And a physicist named Jeremy England explained that maybe life could be a manifestation of entropy. So, like I said, the life could take advantage from the energy that is in the environment to reduce its own disorder. So it's the illustration of the pile of sand, as I said.
Right.
You use energy to form a structure, and you temporarily decrease the entropy. And if you stop providing energy, the sand is returned to its original high mass state. And life do the same with the sun and all the creation of energy in the cells to maintain order within a life, but it requires a constant supply of energy.
Okay.
So this is where it's really interesting.
So just to make sure it's clear, your sand in a pile it was an interesting analogy that you made. But the idea being that, so while we say the second law of thermodynamics says that entropy globally is always increasing or staying the same, it can't decrease.
Yeah.
What you're saying is that, so we can have it decrease in a very sort of limited area, in a local area, but elsewhere, it would increase such that the net effect would be a global increase. So I guess kind of like the way a fridge works, right? Like a refrigerator will cool stuff down. So you put stuff into a refrigerator, it'll cool down, its entropy is going to become lower. So you can say, oh, so we're decreasing entropy. But what happens is that there is heat being ejected by the refrigerator into the environment. So if we take the global entropy of like the kitchen where we have the fridge, then globally, the net result is a global increase, right? And you're saying that life does this. Life is creating order, and by creating order, it is decreasing entropy. But that is happening locally where life is at a cost, which is globally in the universe, it's going to increase the global entropy. Is that it?
Exactly. Yeah, exactly.
Okay. Did you, in your research, at all come across speculation about where life might go, about whether this idea of entropy can help us talk about potential life forming elsewhere in the universe? I only ask because we have another one of your classmates that are going to be talking about life and intelligence elsewhere in the universe, but curious if you came across anything.
For my part, entropy is more like the description, the theoretical description of how life maintain its order. I didn't search about how could entropy have an impact on the apparition of life in others' planets or anywhere else, but I believe that if this is the laws of physics, and normally the laws of physics are working everywhere. So if you have a planet that have the correct position, etc., and all the characteristics to create life, maybe even if it's not on Earth, life could be created and could maintain a low entropy with the use of energy.
Okay.
I don't know if I'm clear, but
no, in any case, your focus was more on the cosmic scale of things and not the on the question of life. Okay, so maybe we can move on to the idea of the different potential ends for our universe. So, which one do you guys want to talk about first? So if I look at my notes, you talked about the idea of the big freeze, you talked about the big crunch, the big rip. Everything is big anyways when we talk about the universe, right? What do you want to go and get into, Marguerite?
Maybe big freeze.
Do you want to talk about the big freeze?
Yeah, we already talked about the big freeze, like the heat death and the big freeze.
Right, we can get a little bit into details of it.
Okay.
So when we talk about the big freeze, is there any proof of it? Is there any way to test to see if that is the most likely outcome for our universe or not? Is there a way for us to observe or to measure something that will allow us to determine whether in 10 to the 100 years the universe is just going to be infinitely big, infinitely cold, and just there's nothing, or no?
We don't have a proof, like absolute proof of really how it could really happen, but we have gathered small proofs and small hints all over the universe and all over studies that can help us in that way, and that corroborate the idea of a big freeze. So, first of all, the idea that the elements are drifting away from each other, then that the galaxies and the planets are being more far away every day from the Earth is really a first hint of this idea, because if we are logical, the more they are getting away, the more they are losing of density. Mm-hmm. And so we used for that some white dwarfs that we are calling candle stars. So they are supernovae that are really luminous, and we have them in the stars and in the sky and the universe, and we are using them as a reference to measure how far the stars are getting away from us, and how fast and how far the universe is like distending and stretching away, I think.
Okay, so what you're saying is that we can observe the rate of expansion of the universe, and based on the rate of expansion of the universe, we can sort of make speculation about if it's going to keep going or if it's going to maybe slow down, if it's going to speed up. And where do we stand on this? What have we observed? What is the most likely outcome from our observations currently?
Currently, we are going in the way of heat death, and just the stars are just getting faster and faster away and away from us.
So we have accelerating expansion.
Yes.
And the question that is going to be to determine is, I suppose, how much supposed dark energy is, because it's the amount of this dark energy which is going to be a key factor whether at some point it's going to slow down or not because of gravitation, right?
Yes, and so since dark energy is invisible, we can't really be sure of how much we have of it in the universe, but today's scientists are saying that it represents around 68% of all the matter in the space.
Or all the mass in the universe.
Yes.
Okay.
So it's really likely to expand.
Okay, so of all the various possibilities, big freeze, heat death of the universe is, at our current state of science, the most likely outcome. Okay. Maybe we can talk also about, you talked about the big crunch theory. I think it was Mathis who brought it up. Do you want to maybe give us a few details of what we mean by the big crunch?
So the big crunch is an hypothesis that tries to explain the end of the universe based on the Big Bang model. So the Big Bang model states that the origin of the universe is from dense and hot states. The Big Crunch proposes an ending where the universe could contract back. It's all in the name, the Big Crunch.
Right.
So it's linked with Albert Einstein's equation of general relativity, which describe how gravity influences the structure of a space-time.
Right.
So the model explains that the universe is expanding, as Marguerite said. We have a lot of observation of this expansion, such as those made by Hubble.
Right. Which have been confirmed and given with much higher precision since the time of Hubble, because that was 100 years ago.
But it's the first, I guess, to observe the expansion. So we know now that galaxies and all the universe is expanding and everything is moving away from each other. So the Big Crunch states and depends on many factors, such as the density of the universe that is clearly reducing and decreasing, but also the nature of the matter. It's linked with dark energy and all the matter that we don't know yet. So the Big Crunch states that the gravitational force could come to dominate the expansion force, and it would result in a gradual slowing of the expansion, followed maybe by a contraction of the universe.
Okay, so the idea is that there are two major forces at play. Gravitation, which is what's going to want to make things come together and shrink, and the force of expansion, which we attribute to this mysterious dark energy. And the question would be to have precise enough measurements to determine whether it's gravitation that's going to win or whether it's dark energy. And if dark energy wins, then it's heat death, big freeze. Yeah. And if it's gravitation that wins in the end, it's going to be the Big Crunch.
Exactly.
Okay. Out of curiosity, did you come across also the Big Bounce theory?
I guess so.
I'm assuming it's the same as the Big Crunch?
The Big Bounce is stating that after all the universe is contracted, maybe we will have another Big Bang that will occur, that the universe will again expand.
Right, so the idea being that the universe is not a one-time thing, it's a cyclical thing. There's a Big Bang, there's expansion, there's shrinking, then there's like the opposite of the Big Bang, which is the Big Crunch, and then we start all over again.
And then maybe when we state that maybe the universe we're living in is following another one that we don't know. So maybe the Big Bang we're talking about 13.8 billion years ago was also a big bounce, and
right, that was the end of another universe that came before.
Yeah.
So we are dealing with science, and science is fundamentally experimental. Are there any experiments, any observations that could be made, that have been made, that could in one way or another help us determine if there has been another universe in the past that went through the big expansion and crunch and then Big Bang again, or no? In your reading, did you come across anything?
For my part, I didn't read anything about this. All we are talking about here is really theoretical and is based on math and laws of physics. And I believe it's really complex in such amount of time, because we're here dealing about, for example, the heat death. We're talking about billions and billions of years. So it's really complex to find a similar states with our timeline, our time period.
Okay, and I guess the idea also being that on the one hand we would need to keep improving our observational and experimental techniques and equipment, and on the other hand improve our theory, and maybe hopefully someday we might have an answer to all this. But at the same time, it's I guess not the sort of question that really we need to answer right away. It's not a life and death question. It's more just for the idea of having an idea of the universe, what it's all about, where it's going, where it's coming from. Okay. I think you guys also mentioned very briefly in your presentation what you call the Big Rip, but you didn't have time to get into it. Maybe we can just go over it in a couple of minutes?
Yes.
Okay, Marguerite.
The Big Rip is sometimes seen as an alternative of the Big Freeze, but whereas the Big Freeze, it is a heat death. For the Big Rip, it is the idea that the expansion of the universe will just lead to the tearing apart of all cosmic elements. So it is the idea that dark energy is gaining an infinite density in a finite time, and so it will tear up the finite time, and it will tear up the time-space fabric, and thus everything in it. So it is the idea that around 60 million before the Big Rip, the galaxies will start drifting apart from each other as they do now, but faster and faster, and they will start to evaporate because of lacking of gravity. And so the planets will then separate themselves from the stars, and the molecules in the planets will just separate, and everything will separate in every scale, and at the end the atoms will become nuclei, and so the separation of everything will lead to a Big Rip, and so the end of the universe.
Okay, so I guess like we've said a few times already, these are all very speculative. There's no real way of actually determining any of all this outside of a theoretical sort of way of looking at things. Okay.
Yes.
How do you guys feel about moving on to some of the questions from your classmates?
Yeah.
All right. So, were there any questions that you particularly found interesting that you want to maybe deal with, or do we just pick at random?
Let's pick at random, I guess.
Let's pick at random. So, a question that I often hear from students, what comes before or after the universe? Or to be more precise, is there something before or after time? How do we answer this question? It's almost a philosophical question.
Yeah, it is. If we take the theory of the heat death, at some point we will have a state of absolute entropy, where there is no more change where the universe cannot be more disordered, and this is a state heat death where the universe is at the absolute zero. And as nothing is changing, we can consider that time itself becomes meaningless, because if nothing changes, we cannot compare the present and the future, or the past and the present. So what comes after the death of time, it's really philosophical.
I think in a way you can even say, I think that's one of the ways of dealing with this question, is to say, I mean, how can you talk about the notion of before or after when those are notions that are anchored in the idea of time? So to say what comes before the beginning of time has no meaning, because before the beginning of time there is no before, there is no time, so you can't use the notions of before or after. A lot of this goes into some very fun aspects of philosophy of physics, which we call philosophy of space and time. There are a lot of really brilliant ideas in there, and lots of fun if you enjoy philosophy. Any idea then, did you guys at all, either of you, when you were reading and preparing for your presentation, come across the idea of this sort of bubble universe?
I do.
Okay,
but,
do you want to maybe talk a little bit about that? What was it? What is this idea of these bubble universes?
I read it, but I'm not quite sure about the info, so I didn't want to talk about it, because
it's okay. Just bring it up. I'll correct you if there's something incorrect there.
So I'm not sure about it.
So this comes from a very. I remember reading about it from this Russian physicist who is well known, Andrei Linde, whose idea was that what we call our universe is just a small bubble, a small piece of a bigger universe, or multiverse, if you want to call it that, where just a little part of it suddenly goes through an expansion and sort of becomes a bubble that's growing, and it's our universe in there. Was that the sort of thing that you came across?
Yeah, I have a picture of many small universes with each with them their own physical laws,
right.
Their different spatial dimensions, and I believe they are completely isolated from other bubble, and they cannot interact with each other.
Okay.
But to me, it seems so theoretical and so
is there any
unlikely
way of,
to exist. So
well, I guess that's where the idea of a lot of the ideas in science fiction for multiverses, that's where they kind of maybe come from, or at least are linked to them. But we're talking something very, very speculative. So Marguerite, you mentioned at some point when you were talking about this wonderful idea of the heat death of the universe, you talked about black holes and Hawking radiation. Do you want to tell us a little bit about what you mean by Hawking radiation?
The Hawking radiation is a concept by Stephen Hawking that say that subatomic particles are emitting from a black hole near its heaven's horizon. So the particles are in pair. There is, if I really understood well, a positive and a negative. So the negative particles goes into the black holes, and it makes the black holes lose energy and therefore mass. So in a bigger scale, if black holes loses more and more energy, it loses more and more mass, and so at the end it evaporates.
Okay, so the idea being that so this is one of the first times we mixed what we call quantum mechanics and the theory of black holes, which is a consequence of general relativity. The idea being that you can't have these sort of random creations of particles and antiparticles, and if it happens in the right conditions, let's say, you can have reduction of the mass of a black hole. The black hole is known for not being able to actually, nothing can escape from it, so it can only grow. But this idea of Hawking radiation came from the 1970s, was that in fact black holes can sort of over time lose energy and therefore lose mass through this process. it would take a lot of time, which is where I think where your 10 to the 100 number comes from during your 5 ages of the universe.
Yes.
Okay. We have a lot of questions about entropy. Obviously, it's a very nuanced notion in physics. I don't know. I think we've talked a lot about it. I don't know if either of you guys, Mathis or Marguerite, if you wanted to maybe come back to the idea of entropy. Any interesting things maybe we didn't go over, or that you found particularly interesting about the idea of entropy?
Maybe just we didn't talk about the unit of entropy.
Okay, sure.
It's
you have the
maybe
floor.
important to just talk about it briefly. So the unit is joule per kelvins in the international
being
system.
the units of energy and units of temperature. Yeah.
Yeah, and it's just the unit to measure the randomness and the disorder in a system.
Okay.
In the second law of thermodynamics.
Okay. Let's look at a few of the other questions. So there was a lot of questions about this idea collapse of the universe, expansion, infinite expansion, and the idea of what could make the difference. If we had to sort of give one key thing that would make the difference between the big freeze and the big crunch, Marguerite, what would it be, do you think?
If we look into the graphs and the diagrams that represent all the theories, there is a really simple explanation. I think it is that the big freeze is really not coming back, and it's a perpetual death
States.
and a perpetual loss of energy, states, whereas the big crunch is coming back to another state of energy, I think, and it's because the big crunch is like a collapsing of the universe, whereas the big freeze is just like non-existence of the universe.
Okay. All right. So I think we're reaching the end of our episode. We've gone 45 minutes. So maybe I'll ask you one final question, the same question I usually ask most of the other guests. How did you find your topic? Did you find it difficult, easy? Were there specific things that really struck you that remained with you that you had no idea about, which you found surprising, or just your general experience in this? Maybe we can start with Mathis.
It was clearly a complex subject, and the part about all entropy and really physics theory is kind of complex to understand. But when you have understood it, all becomes really clear. It's a really theoretical subject, and we're around theories. But I found it really, really interesting, and it's kind of a philosophical question to understand how the universe and how everything that we know, even time, will one day disappear. And
right. I guess this is one of those topics which has literally no applications that could be lucrative, profitable. It's just for pure human knowledge and understanding of the universe. So either you find it completely uninteresting, or I think you find it completely fascinating. Marguerite, what was your experience with this topic like?
I think it was really hard to make researches because since I don't do physics, I was really lost. But same as Baptiste, I think when I started to really to understand the notions, I found it really interesting, and really I was really surprised of how much of numbers, how much of theories, and how much of information we could have imagined about the end of the universe, and how it could, even if it's only just theoretical, but it seems really plausible and really logical. And I think I was impressed by all the work that has been done on the subject, I think.
Okay, so basically the idea that we could even begin to have a way of thinking and dealing and sort of making educated guesses about something that is so infinitely bigger than us and longer in time than us is
yes.
I agree with you. It's something that is quite think that's what draws a lot of us to science and physics, is to be able to sort of touch something that is so much bigger than us in space and time. If it's any consolation, even if you had been doing physics still, I don't think any of the physics that we do in high school would have helped you much with that. So you guys did a really, really good job of it. We all really loved your presentation. It was shockingly good the way you guys were able to explain the idea of entropy, which is not an easy idea to explain even at a university level. So bravo on that. And on that note, thank you guys.
Thank you.
So that is Physics Bites for this week. We hope that you enjoyed this episode, and we would love to hear what you thought about the topic in the comments section. If you did enjoy the show, then subscribe to our podcast, share it with your friends, and be sure to leave us a 5-star rating on whatever platform you're listening on. And more important than all of that, come back soon for a new episode.